Now, what about, so how many total states are there?
2J.
Say again.
Think it's 2J.
It's actually not 2J. Because you're including both J and minus J, okay? So you're counting both of the endpoints. So you get 2J plus 1 states.
Oh, I was counting the transitions, right?
Exactly, yeah. So we get 2J plus 1 linearly independent states. So that means the dimension of that irreducible representation, dimension of the EREP, of the vector space on which the irreducible representation acts, is 2J plus 1. And what about lambda? What about lambda? Well, now I leave it as an exercise for you to work out that J squared acting on lambda n is J plus 1 lambda n. In other words, lambda is J plus 1. Okay. Now, because J is positive, it's a positive number, right? It's a positive half integer. So if I give you J, you can work out what J plus 1 is. So J times J plus 1 is, and vice versa, right? Because if I tell you, oh, this is the J squared eigenvalue, you can just use this formula to figure out what J is, right? So yeah, like solving, this equation has unique positive solutions. So that's why instead of labeling the states by lambda, it is conventional to label, label the states with the eigenvalue J. Okay. Okay, so I think I've come to the conclusion of the formal part, but now we're going to talk about examples and discussions. So are there any questions before we move on to do that?
Yeah, I have a question. So in what sense exactly is this the solution to the problem?
Yes, that's a very good question. You will see. Yeah, in the sense that, I can actually, if you give me a value of J, so that's a value you have to give me. Okay, that's not something that is, that's their problem will determine. Then I can explicitly construct all the operators as well as all the matrices, as well as all the vectors on which this matrices act. I can do anything essentially. Okay.
Using those two equations that we derived earlier.
Exactly. Yeah.
Okay.
And this guy. Yeah, and this guy. Okay, so that's a very good question. So let's move on to that. So I want to give you an example today, which I hope will just completely blow your mind, that how powerful and beautiful this thing is. But before we do that, let's just take stock. And so we're just reviewing. So J can take possible values which are, say, 0, half integers, half positive integers, okay? Okay, in quantum mechanics, this is basically telling you what the total spin of your particle is. And that instead of using, J squared eigenvalue, we use J to label the states or states/vectors, even though J is not an eigenvalue of any operator. Like J is not the eigen, it's just number, so it cannot be, say, an eigenvalue of this, right? This is a vector operator. This is 3 components. So even though J is not an eigenvalue of anything, we use J because we know that if I give you J, you can construct J plus 1 easily, which is an eigenvalue. Okay. So this is a convention. Number 2 is that for a given J, the J3 eigenvalues are J minus 1 ... And this list may or may not include 0. If J is an integer, then it will include 0. If J is not an integer, it will not include 0. So there are 2J plus 1 possible M values. That means that the dimension of the irreducible representation, that is labeled uniquely by J is 2J plus 1 dimensional. Is 2J plus 1. Okay.